Have you ever really thought about the massive language gap between you and the device you're using right now? I mean, we think in words, images, complex ideas, but computers? Well, they live in a much, much simpler world.
And that's the big puzzle we're going to solve today. Think about it. We have 10 fingers, so it makes sense that we count with 10 digits, 0 all the way up to 9. But the most powerful, sophisticated technology on the entire planet relies on just 2, 0 and 1. Why is that? What's going on here?
To get to the bottom of this, we've got to first wrap our heads around this fundamental difference in thinking. It's a real language barrier, but it's not one you can solve with a translation app. It's built right into the physical hardware.
Okay, so let's break this down. On one side, you've got us. We're perfectly happy using 10 different symbols to represent any number we can dream up. But on the other side, you've got the computer. If you could zoom all the way down to its core, it's really just a massive collection of microscopic switches. And a switch can only do two things. It can be on or it can be off. That's it. There's no kind of on or a little bit off. This brings us to a really core concept called a number system. It sounds complicated, but it's just a set of rules for counting. The most important rule is the base, which tells you how many unique symbols you have to play with. For us, with our 10 digits, we use base 10. So for a computer with only 2 states, well, it has to use base 2.
So how in the world do you build an entire language when you only have 2 options to work with? Well, you create a system that's perfectly designed for exactly that. You build the computer's native tongue.
And that system is, of course, binary. Since it's base 2, it only has 2 digits. And here's the elegant part. We just map the switch's off state to the digit 0, and the on state to the digit 1. And boom, just like that, a physical switch now represents a number. Every single piece of digital hardware, from your phone to a giant supercomputer, speaks this language fluently.
So why is binary king? Why this system? Well, for one, it's incredibly tough and reliable. Inside a computer chip, it's much easier to tell the difference between a high voltage for a 1 and a low voltage for a 0 than it would be to try and distinguish 10 different precise voltage levels. Second, it's simple. Transistors are really good at just being on or off. And finally, and this is the absolute key, it maps perfectly to Boolean algebra, the math of true and false, which is the entire foundation for how computer circuits are designed.
So binary is absolutely fantastic for computers. It's their perfect language. But for us humans, it creates a brand new problem. A real headache, actually.
I mean, just look at this. Can you tell me what number that is at a glance? Of course not. It's just a sea of 1s and 0s. It's long, it's a pain to look at, and imagine trying to type that out without making a single mistake.
This was the exact problem early programmers slammed into. How do you work with a computer's native language without getting completely lost in this endless stream of digits? They needed a better way. They needed an interface. And the solution they came up with was truly genius. While we have our decimal system and the machine has its binary system, they created a third system to act as a bridge between the two, hexadecimal. It's a base 16 system, and it turned out to be the perfect compact shorthand for binary.
Hexadecimal, or just hex for short, uses 16 symbols. It takes our familiar 0 through 9, and then it adds the letters A through F to represent the values 10 through 15. Now, the key thing to get here is that computers don't understand hex at all. It's not for them. It's for us. It's an incredibly efficient way for humans to read and write the binary that computers actually understand.
So how does this magic trick actually work? How do we translate between that long, messy binary world and the clean, compact world of hexadecimal?
This is the real aha moment right here. The whole system works because one single hexadecimal digit can represent a group of exactly 4 binary digits, and that group of 4 is called a nibble. So you take a long binary string like 11011010, you just split it into groups of 4, 1101 and 1010. The first group, 1101, is the number 13 in our world, which is D in hex. The second group, 1010, is 10, which is A in hex. So that long, ugly binary number becomes the simple, easy-to-read DA. It's that straightforward.
And this gives us some terminology you'll hear all the time. A single 0 or 1 is a bit. That group of 4 bits we just used, that's a nibble. And a group of 8 bits, which is just 2 nibbles stuck together, is a byte. And the byte is the fundamental unit of data for pretty much every computer system you'll ever use.
But what about going the other way? How do our regular numbers get translated for the computer? Well, it's just a simple process of repeated division. Let's take the number 26. You just divide it by 2 and write down the remainder. Then you keep dividing the result by 2 and writing down the remainder until you get all the way to 0. Once you're done, you just read those remainders you wrote down, but from the bottom to the top, and there's your binary number, 11010.
Okay, so we've covered a good bit of theory. But where does this stuff actually show up in the real world? Why does any of this matter to you?
You actually see hexadecimal everywhere, even if you don't realize it. Ever see a web color code that starts with a hashtag, like hashtag FFF for pure white? Yep, that's X. Each pair of characters represents the amount of red, green, and blue. That same idea of using a compact code is used for things like memory addresses, to pinpoint the exact location of data in your computer's RAM. And for programmers, it's absolutely essential when they're digging deep into software to analyze and fix errors.
So, we started with a pretty simple question. Why do computers only use 2 digits? And the answer took us from physical switches to number theory and into the very language of digital logic. We've decoded the shorthand that bridges the gap between our world and theirs. The really crucial thing to remember is that underneath all the incredible complexity of modern software, there's a simple, elegant, and powerful binary foundation. So, I guess the only question left is, now that you know their language, what will you build with it?